Hello everyone, Namaskar and good day to all. Really feel like missing you all. It's been a couple of months since we have met, and hopefully very soon, as much as possible, very soon we like to meet all our student friends in the campus. And this is a very happy feel, at least to meet all of you through online classes as a part of a crash program for our NEET and CET exams. And today it's day 1. We begin with our second PU, part 1 topics. And before we start our class, 2 to 3 important things I would like to convey. That already we had a very detailed study of all the topics, and in the recent past you have given your board exam. Therefore here, these classes will have a complete brushing of all the key concepts, and I request all of you, while you are following these online classes on your systems, I request you to keep a notebook and don't just be a passive observer, be an active participant, be ready with your notebook and pens. And afterwards, I hope you do remember a very important slogan in our class, that the key words, when you follow the lesson, be very cautious about the keywords, underline them properly, so that even when you are reading any question, that particular keyword should give you a very easy solution. After this class gets over, on the same topic, you will also receive assignments. And as much as possible, I would see that you will receive at least level 1 assignments and level 2 assignments for both CET and as well as NEET. So follow the class with a notebook and pen, and afterwards you do with the assignment, and latter part, for any of your doubts, at the end of the class I will leave my contact, so you can call me and clarify any of your doubts. Now, here comes. Our day 1 program is on the topics of the charge and its properties, then Coulombic force, and a very popular topic of electric field. Let's just remind you about the few properties of the charges. One is the quantization of electric charges, a very popular expression that you all know. Q is equal to plus or minus Ne, that N for an integer, E for the charge of electron, the fundamental charge, right? And of course, loss of electrons, positive sign, gain of electrons, negative sign. So whenever examples you come across where the particles or any conductor losing or gaining of electrons, sometimes they are also called excess of electrons, that is gain, and sometimes they may also term it as a deficiency of electrons, that is losing the electrons. So in all such cases, you will use this Q equal to plus or minus Ne. And then another important property of the charge being the invariance. Invariance, no relativistic effect on the charge of a particle. The masses, the size undergo a change with velocity, but charge on a particle is always a constant, whether it is static or whether it is in motion. This one. And of course, another popular property is expression of charge. So whenever conductor is given charge, all the charge will show a tendency of expelling onto the surface as if somebody is pushing them. So all the charge will come and reside only on the surface of the conductor. So that's what is the expulsion of charge. The other one is the conservation of charge. That is the total net charge. The total charge or the net charge of any isolated system will always remain constant. But when we said as a theoretical concept, as a theoretical question, do remember two important points. This quantization, when it comes, it has a limitation. It is applicable in the microscopic level and it is not applicable in the case of macroscopic level. But whereas conservation of charge, it is valid in all interactions in the nature. There is no exception for the conservation of charge. Now, coming to the popular topic in electrostatics for our CET and as well as NEET is the Coulombic force. I hope you remember this very popular figure and expression. Now here Q and Q2 are two stationary point charges. Do you remember that stationary point charges Q and Q2? R is the separation between them. And in between, it can be either a medium or any other medium. Now this is the popular thing that you know very well. F is the force of attraction between Q1 and Q2. Both may be either like charges or unlike charges. Like charges repel, unlike charges attract, Now this force is a very popular expression. This constant 1 by 4 pi epsilon naught. If numerical value needed for any calculation is 9 into 10 minus 9. Multiplication of charges and denominator is the square of the distance term. Now this is the case for forcing air. For any other medium replace substituted by air, then you are using this one more constant over here in the denominator, this K, the dielectric constant, a very popular thing which also called as relative permittivity. This is called absolute permittivity. No, this is the Coulombic force that you know pretty well. Now the point is how problems arises in the topic. Straightforward substitution and getting answers. And other way of creating some problems in Coulombic force. We have told a number of times, and here I want to show it symbolically. See, examples in Coulombic force will be based on direct substitution, one method, or else. These are the, see how many parameters are there here. Q1, Q2, the two charges. R is the distance term, and then the medium is the third term, fourth term is the force. Now here in this case, any of the parameters change, either 1 or 2 or 3, and ask you to find the changed parameter. That kind of examples were quite popular. And the same I have shown you here. You see here, any of them can be changed, I have told you. Either the charge, change in the charges, change in the distance, change in the medium, consequently a change in the force. And this is what I have represented over here. Hope all of you can see Q1, Q2, the initial charges, separation R and K is the initial constant of the initial medium, and in this case let the force be F. Now here I am showing you, suppose if the charges changes either 1 or 2, any of them. So this is the change in the charge, this is the change in the distance, R becoming R dash. Have used all the primes here, you can see, and K becoming K dash. Now this is what is F dash. Now, any example on the Coulombic force, you can use it as a very stock expression. This F dash, the new force, and F being the initial force. This is what the ratio I have written. Now, whatever changes that are given, you substitute the changes, you get the answer. You get the answer, right? Now, this is completely Coulombic force in the scalar form. Now, the same Coulombic force We need to understand in the vector form as well. Coulombic force in the vector form, if I take, now here I have shown one more time, the Q1, Q2 two charges, and then again the same separation, R is the distance between Q1 and Q2 in the scalar form. Now here, Q1 positive, Q2 negative, unlike charges have taken. Now this Q1 is attracted by Q2 and vice versa, Q2 attracted by Q1. We will find two forces here. The forces have taken, the force experienced by Q1, I am writing it as F12 bar. This is force on Q1 due to Q2, and similarly the force on this other charge, I am writing it as F21 bar. You can see here. So this is what is the force on Q2. Now here, this is the form that I have taken. What we will find in this figure is the force on Q1 is towards Q2. And that is why here what is that taken F12 bar, the vector form. You can find how to write this vector is a very simple but important thing. See the two charges and this is the line joining. You are drawing the vector along the line joining the two charges. Along the line joining the two charges, and how to write that vector direction. It's very simple. You see whether it is attractive force or repulsive force, and that will give you this idea. Now here this F12 bar I have shown this expression. Do you remember how to convert a scalar form into vector form? Multiplication with a unit vector. That's all done. Now this is the form that you get. And please do remember here this is R cube term. In the scalar form you have taken R square term, but it is R cube terms. And this is what is R21 bar. Because this is F12 bar towards Q2 is there. Therefore it is what is R21 bar. Supposing the same, if I take them as like charges, it will be away from Q2. As a result, this F12 bar, here also it becomes R12 bar. Yeah. Here I am with two simple examples for the Coulombic force. Look at this example that I have shown. Here A and B are two conducting spheres. We have shown same size, radius being same, with charges 8 microcoulomb and minus 3 microcoulomb. Separation between them is R, and the examples and the data says the force on A, same as of course force on B. This magnitude is F, and this is all before touching. Now he says A and B, both the conducting spheres, are touched with each other. A and B touched with each other and then separated by same distance. What will be the new force experienced by any of the conductors, either A or B? Now let us see for this example how I make use. As I have to do many examples. Whenever you find the data, change of charge, change of distance, change of medium, change of force. This is a popular expression that I have told you as a simple tool. Now for the same example I am using it. Remember here what is the Q1 happens to be plus 8 units, Q2 happens to be minus 3 units I am writing. This is all before touching, and now after touching, this is I am writing before touching. Now after touching what happens? After touching what happens? That means now here once again we use both conservation of charge and then Coulombic expression. Here when A and B are touched with each other, there will be redistribution of charge such that in this case, following conservation, what is that Q1 dash same as Q2 dash. Remember, these charges become same only if the size of the conductors same. If the size of the conductors are different, no such equal charges will appear. This is the case for, do remember, same size, then Q1 dash is equal to Q2 dash is equal to, I will write Q1 plus Q2 by 2. Therefore now here Q1 dash is equal to Q2 dash will become 5 by 2. 5 by 2. Here you have 8 plus or minus, right? So this Q1 dash equal to Q2 dash is equal to 5 by 2 units, and he says same distance. Therefore now let me use that expression here. Now here I will write what is that F dash by F. is equal to Q1, Q2, that is 8 into 3. 8 into 3 by 5 by 2 into 5 by 2. Do remember, it is a negative charge. But here, this both Q1 dash and Q2 dash will be like charges. Here there are unlike charges and this here is like charge. And then what is the next term we have? R by R dash. No change in the distance. Therefore, I will take that ratio to be 1. And no change in medium. Therefore, that will also be 1. Therefore, what is the new answer? A new force. What is that F dash you see here? This is 4 8s 32. So this is 32 into 3 by 25 times F. Of course, we will get this as negative sign. So it turns out to be 96 by 25 F. And this negative sign shows that F dash and F are of opposite nature. That is, if this F is attractive, F dash is repulsive. If this F is repulsive, F dash becomes. F dash is always repulsive. You should remember in this example. Before touching, it can be either attractive or repulsive. If it attractive becomes repulsive, then you will get this negative sign. Otherwise, repulsive, if it remains same as repulsive, then F dash and F will have the same sign. Like that. So whenever example is given, read the data and see whether what is the change happening in charges or in the distance or in the medium or in the force. One more example I would like to tell you here. One more example, I have taken A and B, two conducting sphere with the charges 3 microcoulomb positive and this is 5 microcoulomb negative. And the example says that excess of 3 microcoulomb is added to each of the spheres, to both A and B. Each of them 3 microcoulomb is added and distance between them is doubled. He says the distance is also doubled and A medium is replaced by other medium of constant K. So the question is, for what value of K the force between A and B remains the same, is it? So one more time, what are the changes that are there? There is change in charge, there is change in distance, there is change in medium, and the example itself says that no change in force. Therefore here, F dash by F equal to 1. Now what is that Q1 dash and Q2 dash? This becomes 3 plus 3 into minus 5 plus 3 by 3 into 5. Now again, distance is, he says, doubled. Distance initially R now becomes 2R. Initially the medium is A and now it is replaced by another medium of constant K. Therefore here I am writing for A, the K value is 1 and the other medium it is K. Now the LHS term is 1. Of course it is square. You will find the answer as K is equal to. Here don't use any negative sign for K, even if you get it in the simplification, don't use it. So here it becomes 6 times 2 by 15 and this becomes 4. Therefore K value you will get it as 12 by you can have this calculation. You will get the value of K here. So that is all. Any example on Coulombic force, look for the data, what are the changes that are happening and substitute in this tool. You will get it. Now let us see one or two simple examples where we use Coulombic force in the vector form. And in this case, it will be a system of multiple charges. That is, a system where we have 3 or more number of charges. Maybe again like charges or unlike charges. And also it can be either collinear charges, that is charges lying on the same straight line, or coplanar charges, that is charges lying in same plane. I'll just show one or two examples here. Now here, whenever we see that multiple charges and Coulombic force, here the simple slogan is draw vectors and add vectors. We have already shown how to draw Coulombic force as a vector depending upon attraction or repulsion along the line of joining the two charges. Now here we will write, we draw vectors and add vectors, and to add vectors again a very simple rule that we have learned in our 11th class, that resultant force is equal to root of F1 squared plus F2 squared plus 2F F2 cos theta, theta being the angle between the two forces. Let me just explain one simple example. Here I have shown a system of coplanar charges in which three charges Q1, Q2, Q3, you can find them at the three corners, the vertices of an equilateral triangle I have placed. And to make it simple, I have taken all the charges as identical charges, each of 2 by 2 balloon, and the side, the distance between any two charges is taken as 5 centimeter. Now here, I will show drawing the vectors and adding them. Now let me take any of the charge. Question can be asked for the net force on any of the charge. Now here I consider this charge at this vertex C. Now at C, this charge is repelled by this charge at B, and also this will experience a repulsion due to another charge Q1 at A. So to show you, if this is the charge at C, then this was the line along which, therefore I will draw one line. This is what is F1 bar, and this is here, this is another force F2 bar. And now since this is an equilateral triangle, this angle will be 60 degrees, and the symmetry of the example shows that same charges and distance between any two charges happens to be the same, complete symmetry. So what you will here conclude is that here this F1 bar is equal to F2 bar, the magnitudes same, and angle between them is 60 degrees. And how do you write F? Of course, Coulombic form, 1 by 4 pi epsilon naught Q1 Q2 by R square. So this will give you the magnitude of the forces. Here both F1 bar and F2 bar, same magnitude but different directions at an angle 60 degrees between them. Now we will substitute all this in this vector addition. F1 is equal to F2 and the theta is equal to 60 degrees. Hope you will do simply on your own. What will be the answer? R is root F square plus F square plus 2F square, and cos 60 of course it is root 3 by, so 1 by 2, 1 by 2, and therefore final answer you will get it as root 3 times F. And what is that F? Of course we have calculated as 1 by 4 pi epsilon given by R square. So in the data, all the values are given, you can just do a simplification and substitute here. So this is one such example where we have drawn vectors and added vectors. And to just one more example, I have just increased the number of charges this time. We made it 4 charges and the geometry is now a square. Here also it is a complete symmetry, all identical charges at the 4 vertices and each side with L. Now supposing if I want a net force on any of the charges, then to consider this charge at B or consider the charge at A. Supposing at A, if I consider, now let me draw all the forces now one more time. A, these are like charges, you will find the repulsive. Draw vectors according to the sign of the charges. So what you will find here is, this is A, this is B, C and B. Therefore now it becomes easy. Repulsion one vector F1 bar, repulsion, one vector away from this charge, and this is also repulsion F2 bar, and this is F3 bar. Likewise, now here you will find three vectors where F1 bar and F2 bar are at right angles, and this F3 bar, due to the diagonally opposite charge, you will find it along the diagonal. Therefore, here one more time, as you can see, we can write F1 bar is equal to mod F2 bar, magnitudes same, and theta is equal to 90 degrees. Therefore, the resultant of mod F1 bar plus mod F2 bar, using this simple convention, you will get it as root 2f, and this root 2f will be parallel to mod F3, parallel to F3 bar. This will be parallel to F3 bar. So what will be the final answer? The final answer we will conclude it as, since vectors are parallel, we can just add them algebraically. Therefore it is root 2f plus f by 2. So this is f times 2 root 2 plus 1 by 2. And what is that f? This f is nothing but 1 by 4 pi epsilon naught. Q1, Q2 means q square. Distance is L square. And of course 2 root 2 plus 1 by 2. So this will be the case of drawing the vectors and adding the vectors. Now in this case, another very popular model for neat and CT would be system of multiple charges, and this time the key word is equilibrium of any one of the charge. The key word. What do you mean by equilibrium? Here we mean it as static equilibrium, where the particle, a charged particle, acted by two or more number of forces in such a way that the net force becomes zero. Like that. So here I have shown the net force, which is a vector sum. Don't forget, net force as a vector sum is a null vector. And I have shown one example. I have taken system of collinear charges. You can find here A, B, C, at which I have placed three charges. This A and C I call extreme charges. Q1 and Q2 both are like. I have shown them as negative charges, and in between B I have shown another charge Q3, which I have taken as an unlike charge. Now here in this case, I will just show one or two cases of equilibrium. Supposing if I have to pay for Q1, what will be the case of Q1? Whether there is a possibility for Q1 to be in equilibrium or not. Now here this Q1, as you can find, is attracted by Q3 but repelled by Q2 because of the like charge. Therefore what you find on Q1 is, this is force due to Q3 is, of course, that 1 by 4 epsilon naught I am writing as K, Q1, Q3 by R1 square. You can see the distance between them is R1, and since these are like charges, it will be an attractive force that is towards Q3. Whereas, now what is that force on Q1 due to Q2? Therefore I am writing the force due to Q2. It is not force on Q2 I am writing, this is force due to Q2, and this is force due to Q3 I am writing. Therefore this F Q2 will be like Q1 Q2 by Q1 Q2 separation is R1 plus R2 squared. Now here, what is that vector you can draw here? Since the like charges, it is repulsion. So this is the vector F Q3 bar, and this is the vector F Q2 bar. Force due to Q2 and force due to Q3, as you can find them in the anti-parallel ways. So two vectors are anti-parallel. So there is a possibility that the Q1 net force may be zero in the case both are equal in their magnitude, because two vectors resulting in a null vector, we need them always equal and opposite. Therefore here, Q1, there is a possibility, we don't say Q1 is in equilibrium, Q1 can be in equilibrium. When these two charges are equal in their magnitude. Therefore, if I make a very small substitution here, so this is F due to Q2 is equal to F due to Q3, then K Q1 Q2 by R1 plus R2 square is K Q1 Q3 by R1 square. A small simplification you will find after cancellation that you have this Q2 by Q3 is equal to Q2 by Q3 is equal to R1 plus R2 whole square by R1 square. This is the condition for this Q1 to be in equilibrium. Similarly, you can verify the conditions for the other two charges, whether there is a possibility or not. Now here in the same case, Q3, you find this I have taken as a positive and the other two are like charges, right? Therefore Q3 attracted by Q1, therefore it is towards our left hand side, your left hand side, and due to Q2, the force is due to your right hand side. Right? Therefore again at B also, Q3 experiences two forces in opposite direction. Again, two forces in opposite direction. Possibility for equilibrium. If they are equal, then equilibrium exists. But for the possibility I am speaking, two forces, opposite direction, possibility. Therefore, again the same condition if I apply, what is the condition this time? Force due to Q1 is equal to force due to Q2. This is I am writing it for the charge Q3. So what is the force due to Q1? I will take that as K, Q1, the middle charge Q3 by R1 square is K between Q2 and Q3, therefore is K Q2 Q3 by R2 square. A simplification will tell you that Q1 by Q2 is equal to R1 square by R2 square. Now in this case, this middle charge can be equilibrium. The same way you can also check the equilibrium for the other charge C as well. Therefore in this case you will find that there is a possibility that all A, B and C, any of them can be in equilibrium. Remember I have told any of them can be in equilibrium, not all of them. Sometimes there is also possibility that all the charges can be in equilibrium. Of course, in the case of all identical charges, we'll give it as an example in the assignment, and also in the hints and solution you can find the answer.